If the charge is moving but it's not in a wire, just an isolated point charge flying through space, if that moving charge enters a magnetic field, there's a force on it as well. We'll do the math this time first. It's a variation of our ILB equation. We replace the I with Q over T, and then we can replace the L over T with V, so we get QVB multiplied by the sine of the angle. For the numbers given in this one, I just made them up. We've got a charge of 2. It happens to be negative, but I'm not going to worry about the negative yet. I'll deal with that when I'm doing my left-hand, right-hand rule. It says it's going at a speed of 50, and it enters a magnetic field of 2. 2 is a strong magnetic field. Just looking at my directions, a particle is moving away and the magnetic field is pointed to the right. That means that my angle is 90 degrees. Sine of 90 is 1, so I don't even really have to worry about that. When I multiply it out, I get 2 times 10 to the negative 4 newtons. Now switching to left-hand, right-hand rule, again, it's tough to draw this stuff on an iPad, but it says it's a negative particle, so I'm going to use my left hand. From my perspective, the particle is moving away from me, so I would draw that as an X. It enters a magnetic field that is pointed to the right, and I want to know what direction the force is. So with your left hand, point your left thumb, high five hand, point your left thumb away from you to match the magnetism. It says the magnetic field is pointed to the right. So with your left hand and your left thumb pointing away from you, point your fingers to the right. When you do that, you should end up with your palm facing upward. So for this one, the value of the force is 2 times 10 to the negative 4, and I would say that the force is